Hey everybody, Mr. Vels here. This is Precalc A, February 21st, or it's probably sometime in the middle of February for you guys. February 21st, 2021 here, still in the middle of this whole COVID pandemic stuff. Videos for you, hoping this will help out. Today we're looking at logarithmic laws, and then we're going to do some something called re-expressing data. So you definitely need your graphing calculator with you today, and we're going to give this a shot. So here we go. So the first thing I'm going to start off with is the 4 basic log laws. If you want to pause the video, copy those things down. Let me go ahead and pull that sheet out. That's kind of going through the screen on this. The 4 log laws that we're going to talk about basically is a product law. Says that if I multiply 2 numbers together, I could write them individually as the log of their individual sums. So the example on this, the log 2 plus the log of 4 equals the log of 8. So I can take a single log and break it up into smaller logs, or I can take a couple of different logs and write it as a single log. And they all have to be the same base. So if this was a base of 3, this would have to be a base of 3, this would have to be a base of 3, or a base of 10, 10, and 10. I've just written most of these ones right here with no bases until I do this one, which is called the change of base law. That also means that I could write the log of 8 actually as the log of 16 plus the log of a half also equals the log of 8, because since it's a product thing, 16 times a half is 8. So that's the first log law. The second one says that if I take 2 logs and I subtract them, that's the same as a singular log of their quotient. So let me write them backwards this time. So log 32 is equal to the log of 64 minus the log of 2. Now I could also write the log of 32 is equal to the log of 96 minus the log of 3. Or if I wanted to get fancier here, I could do it as the log of 8 minus the log of 1/4, because 8 divided by 1/4 is 32. Again, not divided by 4, right? That of course would be 2, but 8 divided by 1/4. So how many quarters go into 8 whole things? That'd be 32. Okay, so this is the one that should be familiar for me from data A, because of all the times I said it. This is called the log-ride law, and the log-ride law basically says that anytime you have a logarithm of a base raised to a power, that we can change this from an exponential situation, this power situation, and that base can run right down there in front and become a linear situation. And that's the awesome thing that allowed logarithms to help us solve exponentials. So let me give you a quick little example of how that works. If I put the log of 3 squared equals 2 log 3, you're like, oh, that hopefully makes sense, right? So let me write it another way and see if you agree that this is why this thing would work. So if I wrote this as the log of 9, I'm hoping that you would say by log law number 1, I could rewrite that as the log of 3 plus the log of 3, because 2 sums of logs equals the log of their product, yes? And if there's a log of 3 plus another log of 3, that's 2 logs of 3, and now you can see that that is the same whether or not you write it like that or like that. Okay? The last one, something like this. Let's say I took the log of 16 base 2, and I want to know what that equals. Well, if I wrote it like this, you'd be like, oh, that's pretty easy. I can do 2 to what power equals 16. You'd be like, x equals 4. Yay, smiley face. I can do this math in my head. I don't need anything. So then I go, okay, awesome. Let's try this one. Log 30, base 3 equals what? And, so many of you are like, oh, it's 10. Yes. Nope. Because when we rewrite it, we're doing 3 to the x equals 30. And 3 to the 10th power is not 30. 3 to the 10th power is flipping big. So what I need to know is this, see if this makes sense. If x was 3, it'd give me 27. If x was 4, it would give me 81. So I know if I'm trying to get 30, I got to get somewhere between 3 and 4 for my exponent. A lot closer to 3. I mean, it's going to be like 3.06 or something. I don't know. That's my guess. So how else could I do this? Well, log number 4 says that if you have a base where it doesn't just work out nice in your head, or you don't have the log base on your calculator, then you can do this. You can rewrite it as x equals the log of 30 over the log of 3, just like that. Okay, so let's check it. Remember I said that I believed it was going to be somewhere between 3 and 4. So I turn my handy dandy calculator on, and I do the log of 30, close parentheses, that's really important, divided by the log of 3, close parentheses, and I hit enter. 3.095, right about where I was thinking, just a little bit above 3. Cool. Now remember, on your calculator, if you have this special button right here, A, which not all the calculators have, you absolutely can just put it into there just like that, and hit enter, and you'll see that it will get you the exact same number. Just trying to understand how the math gets you to those numbers. So what happens if I have something like this, log of x squared y cubed over z to the 4th, something like that. And I wanted to expand this. I'm like, hey, that's a single logarithm. I want to break them up into smaller logs. Well, I'm hoping that you know that you could use the log laws above and rewrite it as the log of x squared plus the log of y cubed minus the log of z to the 4th. Because multiplication becomes addition and division by z comes subtraction. Then you're like, ooh, I could use log number 3 to rewrite it like this into log x plus 3 log y minus 4 log z. Yep, 100% that you could do that. Now, if I had something like this, log of 64 over 16, I could 100% write this as the log of 64 minus the log of 16. I could do it like that. Remember that that is not the log of 48. Nope, 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 nope. Cannot do that. Does not equal log 48. It's not how that stuff works. However, another way that I could do this is, maybe if this makes sense, that 64 over 16 is 4. So I could rewrite that as log of 4. And look at that. You can already see it doesn't equal log 48. It's log 4. But if I kept going, I could rewrite that as the log of 2 squared, right? And if I kept going there, then it would be 2 log 2. And now I've simplified it so the smallest number possible is the logarithm. And that's really how people before technology used to solve these types of things. Okay, so that's basically your log laws. They'll be really helpful as we go through different stuff in the future. We could do this. We could take something that's condensed and expand it, or we could take something that's expanded and condense it, so moving back and forth on that. There'll also be some in the homework, some more stuff on decibels. And I believe there's something on light intensity too. Let me check my stuff. Lumens, yep, some stuff on lumens. So really on those ones, they're just applications. The lumen the lumen formula, I think it just gives you an equation, so just make sure that you use that. And if it says, I believe the problem in the text says this, log of 1/12 equals negative 0.00235x. It's like that. So don't lose track of the fact that this implied little number down here is a 10. So if I wanted to rewrite this as a exponential equation, it'd be 10 to that power equals 1/12. Like that, you can go from there. Okay? So that's the first part of it. And the second part, this stuff you're going to really need your graphing calculator for. This is on re-expressing data. And it's going to take us a little bit to go through this, so have your handy dandy calculator. Again, pause the video, copy these down one at a time, and I'm going to talk you through a bunch of different stuff. Okay, so first, you should be able to see that. I'm going to go ahead and turn that on. I'm going to go second plus sign number 4, clear all lists so that those are all done, clear that out. Go to my y equals, clear out any equations, go to my stat plots, turn any of my plots off, all of those things. Stat, edit, and let's plug it in. So I got data here first, 2, enter, 4, enter, 9, enter, 14, enter, and 18. Enter just like that. And then L2, 3.1, enter, 4.88, enter, 14.9, enter, 45.475, enter, and 111, enter. Okay, so what's the big picture on what we're doing with this thing called this re-expressing of data? You guys know that we have a wonderful capability on our calculators called regression analysis, and we can find equations of best fit that way. Well, this is going to look at specifically another way to look at it besides using your R values, your correlation coefficients. So first thing I'm going to do is my x's are going to go from 0 to 20. My y's are going to go from 0 to 112. Okay? So on my window, 0 to 20, my y's are going to go from 0 to 120, like that. And I turn my stat plots on, boom, L1, L2, and graph. So you can see I got a little curve going on here. So my question is this data exponential, or is it quadratic, or is it power? What is it? Because it's curved, it definitely goes up. Maybe it's even logistic. I don't really know right now. Well, there's a way to be able to tell by re-expressing data, and you've got to pay really careful attention to it right now. So what we're going to do is this. We're going to hit stat, we're going to hit edit, and we're going to redo stuff here in L3 and L4. And the first thing I'm going to do is this. Watch. I'm going to go to L3. I'm going to hit my up arrow. I'm going to hit enter. And that pops the little cursor right down here. But it also makes it an equation. So now I'm going to type in second L1, and you can see that it copies that entire line of data again. So poof, there's my X data. And then L4, I'm going to do this. I'm going to go up. I'm going to hit enter. And again, that's there. Awesome. Except this time, instead of just copying L4, because they look identical, right? I'm going to do the natural log of L4. And again, those little L1, L2, L3s, L4s are nothing more than the see the little buttons above 1, 2, 3, and 4. Okay? Parentheses, and I'll hit enter. Oop. To go to that was dumb. Did you see that? I really want the natural log of L2. Oops. That's what happens. I'm like, why is there an error? There shouldn't be an error with my data right now. Awesome. So you can see that. Are we good with that? Okay, so now what I want to look at is, instead of looking at L1 and L2, I want to look at L3 and L4. L3 and L4. So when I go here, second stat plot, and turn it on, I'm going to go L3 data and L4 data, just like that. And on my window, you can see that my stats for my Y's changed. And fun fact. Let me take you back to that real quick. Stat edit. They go from 0 to 5, basically. So on my window, I can go 0 to 5 on that. And I'm going to hit graph. And what do you notice about that data? Sweet. Yes, it is a straight line. Okay, so here's your big if right now. If when you re-express the data, if XY data is re-expressed as x comma ln of y, and it becomes linear, if it becomes linear, then the data is exponential. That's a fact. Data is exponential. If when we take the normal x and the normal y and we graph it again as x and the natural log of y, and that becomes a straight line, then the data is exponential. Now watch. Stat calc exponential regression L1 L2. Look at that R value. Isn't that amazing? That is an amazing R value. Now watch stat calc. Number 4, linear regression for L1, L2. Is that as good of an R value? Nope, not as good of an R value. Stat calc. Number 5, quadratic regression. Is that a good of an R value? Nope, that's not as good of an R value. Stat calc, and you're like, but wait, Mr. Bells, look at this one. Quartic regression, yeah. Look at that R value. It's 1. That one's better. No, it's not better. Remember, I only gave you 5 data points, so with 5 data points, a degree 4 polynomial will always fit it. So don't just assume something is right because you went up in your regressions. It is exponential. And it's exponential because that stuff was linear. Okay, so here we go. Stat, edit. I got all this stuff in here. I need it to all go poof. All go away. Second, plus sign, number 4, clear all lists, all done, stat, edit. Look at that. It's gone. We do this data now. This data right here. So 7, enter 57, enter 187, enter 267, enter. Now I chose this one, but I could have chose other data too. 457, enter, and then why the heck is it over there? My bad. So look at how quick I can do this. L1, enter, second, L4, look at that, I just copied it over there. L2, 22.01, enter, 26.49, enter, 28.985, enter, 29.73, enter, 30.86, enter. Sweet, so before I go look at this L4 stuff, I'm going to turn my stat plots back on. L1, enter L2, enter. You should be really good by the time we get done with all this stuff this way. Okay, so on my window, my x's again go from 0 to 500. I'm going to put that, so 0 to 500. And my y's go from like 20 to 35. We'll do that 20 to 35 graph. So that looks like that. Boom. That could be a negative exponential function, right? It could be an upside down parabola. It could be all kinds of funky stuff. I don't really know what's going on. Maybe it's a logarithmic equation. So stat calc. Let's try it. Let's see what a natural log regression looks like on this. Look at that. Look at that data. Isn't that amazing? That's really solid. So what about this re-expression? Because remember we said we weren't going to use the R values. I'm just showing you these to let you know why it actually does work. Stat calc. Let's try this again. Edit. And let's redo this. So L3 enter is L1. Let's see if the same thing works for this. And then L4 is going to be enter the natural log of L2, enter. So now we're going to try and do those, and that's 3 to 3.5. 3 to 3.5. Is that good? So second y equals plot number 1 on L3, enter L4, enter, and window. Remember, this was 3 to 3.5. That's pretty small stuff, right? It's a pretty small window. Look. Oh, it wasn't linear, was it? And some of you are going like, duh, Mr. Vowels. If it was linear, right? If it was linear, then the data was exponential, and that definitely didn't look exponential, did it? So how does this one work? So stat edit, we're actually going to do this, okay? So to check to see if it's a logarithm, okay, remember this one was exponential. To check to see, it's going to be a linear thing again, so it becomes linear. Then the data is logarithmic. You're like, well, what happens? Because it's definitely not xy, x, ln, y. So it's xy, and it's actually this. I haven't showed it to you yet on the calculator. It's actually the natural log of x comma y. Okay, and if that becomes linear, then it's a logarithmic. So let's check it out. So L3, good deal right here, right? Hutch, clear. L3, we're going to hit enter, and then we're going to hit natural log of L1, and then L4, we're going to have it be just the regular y, so L2. Okay, so L4, remember I go up arrow, I hit enter once, and now it's going to become an equation, and I do L2. So my data is going from 0 to 7 and 20 to 35. 0 to 7 and 20 to 35. 0 to 7 and 20 to 35. 0 to 7, 20 to 35. And graph, look at that, straight line for that. Okay, awesome. So we're doing 3 different data sets. Here's my third data set. You guys know that we've talked about power functions, right? Power functions are like x to a power of 3/5, or x to a power of 2/3, or x to a power of 3.712, whatever it is. And there could be some number in front here, whatever it is, I don't care what it is. But not a perfect quadratic, which is degree 2, not a perfect cubic, which is degree 3. Put something in between those, where it's a number multiplied to an x raised to some power. Okay, those are called power functions. And the data is a power function if this is true. If x comma y is re-expressed as ln x comma ln y. So you do it to both of them, and that becomes linear. Okay, so again, this data was exponential because when I re-expressed it as x comma ln y, it became linear. This data is logarithmic because when I re-expressed it as ln x comma y, it became linear. And this data, I believe, is going to be a power function if when we re-express x and y as ln x, ln y, it becomes linear. So I'm hoping, why don't you try this? Pause the video. Give it a shot. Plug it into your calculator, like do all that stuff and see if it actually is a power function, whatever the power and the base is, and stuff. Okay? Yep, pause the video, try it. Okay, so I'm back again. We're hoping that you actually did that, and this is just a quick review for you. So I'm going to go second plus sign number 4, clear all lists, poof, stat, edit. Yeah, we're going to rock this stuff out quick, right? 2, 5, 8, 15, 25, 2, enter 5, enter 8, enter 15, enter 25, enter, yay, L2. 12.73, enter 50.3, enter 101.8, enter 261.4, enter 562.5, enter, just like that. Is that good? Put that so that's a little bit straighter. I'm even going to move this down a little bit so you can see this all. Okay, now, I'm going to check, quick look at the window, stat plot on L1, enter, L2, enter, just so you can see it, and my data goes from 0 to 30, 0 to 30, and Y value goes from 0 to 600. I'll go 0 to 600. Oop, let's skip one. 0 to 600. Definitely got some curvature, right? A little curve. It's not a straight line. It's got some little curve. Like, is that exponential curve? Is that quadratic curve? Is that cubic curve? What kind of curve is that going on? So we said, I believe that if I do this, right, stat, edit L3, enter is natural log of L1, and L4, enter is the L4, enter is the natural log of L2, poof. But if I graph those data points and I plot them, I believe it's going to be linear if this is a power function. If it's not linear, then it's not a power function. It's not linear. So let's go 0 to 4 and 0 to 7. 0 to 4 and 0 to 7. I'm looking at them before I go to my window. So 0 to 4 and 0 to 7. And some of you are going to hit graph right now and you're like, I can't see it, I can't see it, I can't see it. What's going on? Remember that this data isn't in L1 and L2, it's in L3 and L4. So second L3, second L4, poof. And again, remember, that's what's awesome about this. You could slow this down, you could slow the speed down on it, you could put it at half speed and that would talk really funny. Or you can just pause it so that you can get whatever you need to out of this. And I hit graph and look at that. That's a straight flipping line, isn't it? Sweet. Now I'm going to, so it did work. Check, check. I'm going to show you here. Stat, calc. Let's try power regression. Poof, 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 poof. Poof. 0.999999941. Isn't that awesome? Stat, calc. Let's try quadratic regression. 5. Not quite as good. Good. Not quite as good. And it should be pretty similar, right? Because powers and quadratics are similar. Stat calc. Let's do that power regression again and make sure that you understand what the actual equation is so you can see. So my leading coefficient is 4.5. My power is 1.5, so it's kind of like raised to the 3/2. So it's about 4.5 times x raised to the 3/2 power. So I cube it and I square root it to get the value. So I take any number, cube it, I square root it, and multiply by 4.5. So let's just try this, see if it works. 8 raised to the 3rd power, enter, cubed it, and then raised to the 0.5 power, square root it, good, and then times by 4.5. And 101.82, 101.8, that's good. Those were just rounded numbers. So I'm hoping this was great. I'm hoping you understood all the stuff that goes involved in this, and you learned some more stuff about your calculator and what re-expressing data is. So reminder, we covered 4 log laws, right? Log of x plus the log of y equals the log of their product, xy. Log of x minus the log of y equals the log of their quotient, x over y. That log of x to any power, like x to the 3rd, is equal to 3 log x. That's a log right, and you can bring it down. That on any log, when you have a base other than 10, or e if you're using a natural log, you can, like say you have log of 8 base 5, you can write that or evaluate it as log of 8, close parentheses, divided by the log of 5, close parentheses. That's your 4 log laws. And then all this stuff on re-expressing data. Basically, how can we use logarithms to help us understand if the data is exponential, first situation, logarithmic, second situation, or a power function, third situation. Good deal. Hope you guys are staying on top of this stuff. Again, always here to help. We'll talk to you later. Bye.